Welcome to the Deep Dive, where we unpack fascinating topics from the sources you share with us, transforming complex information into surprising nuggets of knowledge and insight. Today, we're taking a deep dive into something you might never have given a second thought: lighting technology. Specifically, a truly ingenious yet surprisingly obscure innovation known as induction lamps, sometimes called electrode-less fluorescent lamps.
Yeah, and what's truly fascinating here is how a concept, simple in its fundamental principle and understood for over a century, took so long to become practically viable. And perhaps even more curious why, despite its incredible potential and a rated lifespan that sounds almost unbelievable, it never became a mainstream lighting solution. Our primary source for this deep dive is an incredibly detailed transcript from a YouTube video that really brings this story to life.
So our mission for you today is to peel back the layers of this brilliant idea, explore the ingenious engineering that brought it to life, understand its unique, almost futuristic advantages, and ultimately piece together why this bright idea didn't quite light up the entire world. Okay, let's unpack this fascinating history.
Right. So you're undoubtedly familiar with the long, glowing tubes of conventional fluorescent lights you see in offices, kitchens, or workshops. You know, the ones with those little black ends, which are actually wires, pins, and electrodes. Those electrodes are critical. They're what spark the gas inside and make the tube glow. But imagine a fluorescent lamp that's just a simple glass tube, completely sealed, with no wires, no pins, and no internal electrodes at all. How in the world would you get that gas inside to light up? It seems to defy the very definition of a fluorescent lamp.
That's precisely the central puzzle, isn't it? If there's no direct electrical connection, how do you excite the gas within the tube to create light? It forces us to think beyond conventional circuits. And this is where the real cleverness comes in, a principle many of us might remember from a physics class, or maybe vaguely remember. Instead of internal electrodes, these induction lamps use a pair of external coils. You can think of them like miniature electromagnets, technically ferrite cores wrapped tightly with wire.
Right.
These cores are placed on either end of the glass tube.
And within a sophisticated driver unit, a high-frequency alternating current is fed through the wires wrapped around those ferrite cores. This rapid, high-frequency current causes a magnetic field to rapidly form and collapse within the cores. If you consider the underlying principle, it's essentially a transformer design, but one where the secondary coil isn't a physical wire winding at all.
Right. In a typical electrical transformer, you have two coils. The primary coil where you put the power in, which then creates a magnetic field. That magnetic field then induces a voltage in a secondary coil, transferring the energy. But in an induction lamp, as you said, there's no physical secondary coil. So how does the energy transfer happen?
Well, what's truly ingenious here is that the fluorescent tube itself, or more accurately, the gas inside it, becomes that missing secondary winding.
The gas itself.
Yeah. Once the glass tube is positioned within the rapidly changing magnetic fields generated by those external cores, the gas in the tube forms a closed loop. The fluctuating magnetic fields induce a voltage and current flow directly within that gas loop, causing it to ionize and light up. It's pure electromagnetic induction at play, without any physical contact with the light-emitting element.
So the actual light production process, once the gas is excited, is fundamentally the same as a conventional fluorescent lamp.
Correct.
Mercury vapor and a noble gas get energized. They emit ultraviolet light, and then the phosphorus coating the inside of the tube convert that invisible UV light into visible light. But the method of getting the current through the gas, that initial spark, is entirely external via electromagnetic induction, which of course gives these lamps their name. Induction lamps. Yeah. Okay, so beyond just being a neat party trick, what was the driving force behind pursuing such a complex design? Our source highlights a particular 200-watt induction lamp with a massive output of 16,000 lumens.
Yeah. Huge output.
That's incredibly powerful and bright for a fluorescent, especially for its relatively compact size.
Yeah.
But that wasn't the main game changer, was it?
Not at all. While the brightness was impressive, the core advantage, the singular reason for all this engineering effort, was the operating life. You see, the Achilles heel of conventional fluorescent lamps has always been those very electrodes we just discussed.
It's the wear out.
Exactly. They slowly degrade over time through a process called sputtering. Each time you turn the lamp on especially, a tiny bit of material flakes off the electrodes. This sputtering causes those familiar dark spots you often see at the ends of old fluorescent tubes, and eventually it leads to lamp failure. Traditional fluorescent tubes typically maxed out around, 10,000 hours of operation, maybe a bit more sometimes.
So by eliminating the electrodes entirely, you've essentially removed the primary failure point.
Precisely.
The tube itself is just a sealed glass vessel with some phosphor coating gas and a tiny mercury pellet. There are no moving parts to wear out, no filaments to burn out. It sounds like you've created a practically immortal light bulb.
In theory, yes. The tube itself has a theoretically unlimited lifespan because that sputtering mechanism is gone. Now, while the phosphor coating does degrade over an extremely long time and the mercury can get absorbed, these lamps were rated for an astonishing 100,000 hours of operation.
100,000 hours.
100,000. To put that in perspective, that's a tenfold increase over traditional fluorescence. If you operated one of these lamps dusk to dawn, say 12 hours a day, it would last for nearly 23 years before you'd even think about needing a replacement.
23 years for a single bulb.
Yeah.
That's just a mind-boggling number. Given that kind of incredible lifespan, it begs the question, why aren't these lamps everywhere? Why aren't our offices, streetlights, and homes illuminated by these seemingly indestructible sources?
That's the million-dollar question, really.
Now, what's really intriguing is that the basic principles of electromagnetism have been understood since the 19th century. In fact, none other than Nikola Tesla himself was experimenting with electrodeless lamps over 100 years ago.
That's right. Tesla was way ahead of his time on this, too.
So if the science was there, why did it take until 1967 for someone named John Anderson to patent a lamp like this, and then another 2 decades until 1990 for it to finally be commercialized by companies like Philips? What was the holdup?
Well, it's a classic example of simple ideas often hiding incredibly complex engineering challenges. Inducing a current in a gas loop is vastly more difficult than in a solid metal wire. It required sending incredibly high-frequency alternating currents through those external coils.
How high are we talking?
Frequencies that sometimes reached the AM radio broadcast band between 100 and 500 kilohertz. So pretty high for power electronics back then. The problem was early core materials like ordinary iron simply couldn't handle those extreme frequencies. They would get incredibly hot from what are called eddy currents.
Ah. Essentially wasteful swirls of electrical energy induced within the core itself. The breakthrough came with the development of ferrite compounds in the 1930s.
Right.
Ferrites are magnetically permeable, meaning they can efficiently guide magnetic fields, but crucially, they're not electrically conductive. So they eliminated those wasteful eddy currents and the overheating. However, ferrite was expensive.
Always a catch.
Always a catch.
Yeah.
Which influenced designs to minimize its use, leading to lamps that narrowed where the core is attached, for instance.
Okay, that makes sense. And then there's the even more fundamental mystery of how these lamps actually start without electrodes. Conventional fluorescent tubes use heated electrodes to ionize the gas to get that initial electrical path going.
Mm-hmm.
Our sources mention some early patents that included things like conductive strips for ionization, but the actual commercial lamps don't seem to have them. So how do you kickstart a glow from nothing? That's a great question, and even the patents are a little vague on this. The best explanation we have is that the driver circuitry at startup sends a much higher initial voltage, a big jolt.
Okay.
This creates an extremely strong electric field, strong enough to throw about any free electrons naturally present in the gas, causing some initial ionization. It's almost like how a fluorescent tube will glow when you hold it near a Tesla coil, you know?
Ah, yeah, I've seen videos of that.
Right. Once enough gas particles are ionized and become conductive, the arc discharge can begin, and the lamp glows steadily from the induced current.
Right.
It's quite a clever trick, even if the precise physics of that initial ionization remains a bit of an engineering handwave.
Okay, it's still a bit mysterious.
Yeah.
Now, here's another curious twist in the story. The first commercial product, like Philips's QL line and GE's Genera lamp from 1994, looked nothing like the linear tube shape we've been describing.
Not at all.
They actually resembled ordinary incandescent light bulbs, those familiar pear-shaped or floodlight-style bulbs. How did that happen?
Well, it makes perfect sense when you look at how they were constructed. These were essentially built inside out.
Inside out.
Yeah. Instead of external coils on a linear tube, a single induction coil protruded into a hollow, spherical, or conical glass vessel. When energized, this internal coil created a kind of fuzzy donut of UV light inside the glass.
Oh, okay.
A bulb shape could then perfectly encapsulate this, creating a compact, powerful, and long-lived fluorescent alternative that conveniently mimicked the form factor and appearance of incandescent reflector bulbs. This was a really compelling aesthetic and functional advantage, as it meant they could screw directly into existing fixtures.
Right, ease of replacement. But these internal coil designs must have had their own unique set of challenges, wouldn't they? I imagine sticking an induction coil inside the bulb would generate quite a bit of heat right where you don't want it.
Absolutely. The induction coil itself, being so close to the gas and enclosed, got extremely hot. This heat could actually reduce the ferrite's magnetic performance over time, making the lamp less efficient.
So less light, more wasted energy.
Exactly. Philips addressed this in their QL lamps by incorporating a clever heat-conducting material into the core stem, what they called the antenna, to draw heat away. GE, in their Genera lamp, didn't seem to have such an elaborate cooling system, though their lower wattage might have made it less critical for them.
Interesting difference.
Beyond heat, there was another significant hurdle. These internal coil designs often required even higher operating frequencies, sometimes around 2.5 megahertz.
Megahertz. Wow.
Yeah, getting up there. And pumping dozens of watts of power at radio frequencies meant radio frequency interference, or RFI, became a major problem. These lamps were effectively broadcasting on the radio.
Seriously. So you're telling me these lamps could literally interfere with someone's radio, maybe even disrupt vital communications?
Potentially, yes.
That sounds like a pretty big red flag, especially for a consumer product.
It absolutely was. The source even highlights that GE wasn't exactly making strong promises about RFI effectiveness. They explicitly warned against using these Genera lamps on boats, for instance, due to potential disruption of maritime communication.
On boats. Okay, that's specific.
Yeah, and they even provided a dedicated phone number for interference complaints.
A complaints hotline for a light bulb.
Pretty much. It sounds less like a fully polished product and more like a high-stakes beta test in the wild.
Yeah. Here's our new bulb. Hope it doesn't jam your radio. So, despite this astonishing 100,000-hour lifespan and genuinely clever engineering, the technology largely remained obscure. Was there a grand conspiracy to keep these lights out of our homes? Probably not, right? It almost always comes down to the market.
Indeed, no conspiracy necessary. It simply came with some significant downsides that prevented mass adoption. Firstly, cost. The Philips QL line was a specialized commercial product, incredibly expensive. It only made economic sense in very specific high-maintenance applications where relamping was a massive operational headache than remote lighthouses, or in specific safety-regulated environments like the oil and gas industry where scaffolding costs for bulb changes were prohibitive.
Places where changing a bulb is a major operation.
Exactly. The GE Genera, while more consumer-focused, still retailed for about $30 in 1994.
$30 in 94.
Which is equivalent to about $65 today. That's a lot for a single light bulb, especially when its actual expected life wasn't always a dramatic improvement over existing fluorescents if the internal electronics failed.
Ah, that's a crucial distinction. While the tube might theoretically last forever,
Right.
the sophisticated electronics in the driver unit, like any complex electronic component, weren't guaranteed to last that full 100,000 hours. So the system was still only as strong as its weakest link.
Exactly. The driver could fail long before the tube itself gave out. Secondly, there were issues with light quality and directionality. While longer-lived, it was still fundamentally fluorescent lighting.
Which means?
Which meant a kind of light quality for many applications, and critically, fluorescent lights are not point sources. Their light is diffuse.
Spread out.
Spread out, making it incredibly hard to direct into a narrow, focused beam. For applications like street lighting, for example, you'd need many more fixtures placed closer together compared to high-intensity discharge, or HID, lamps which could throw light much further.
Okay.
The Genera, despite mimicking an incandescent flood bulb's appearance, simply couldn't replicate its directional light, which is crucial for effective illumination in many fixtures like spotlights or downlights.
So even with that lifespan, they still struggled on fundamental performance aspects. And then I'd imagine conventional fluorescent technology wasn't just sitting still either, was it?
Not at all.
Nah.
As induction lamps were trying to find their footing, conventional fluorescent technology saw its own significant innovations.
Huh.
Electronic ballasts for traditional tubes became commonplace, providing flicker-free light and dramatically increasing energy efficiency.
Right, the flicker was always annoying.
In fact, a bog-standard T8 tube with an electronic ballast quickly became more energy efficient than many of these induction lamps.
More efficient, wow.
Yep. And then, of course, came the compact fluorescent lamps, or CFLs.
Ah, the swirly bulbs.
The swirly bulbs. Once CFLs became cheap, widely available, and offered acceptable light quality in a compact screw-in form factor, small induction lamps just didn't make economic sense anymore. The market, in its wisdom, clearly decided the elegant electrode-less design wasn't worth the extra cost or the compromises. In many ways, this entire discussion about lighting technologies that battled it out for dominance is now largely, well, moot.
Yeah, because of LEDs.
Exactly. The LED, or light-emitting diode, has come along and trounced virtually every lighting technology that came before it in terms of energy efficiency, light quality, incredible flexibility in design, and rapidly falling costs.
Yeah.
General lighting, for the most part, is now what we might call solved.
That's very true. But even though LEDs are the dominant solution today, it's fascinating to look back and see that our path to these modern lighting solutions was filled with all sorts of ingenious, sometimes wacky nonsense like induction lamps.
Definitely some wacky nonsense along the way.
They certainly pushed the boundaries of what was possible, solved problems in incredibly clever ways, and undoubtedly taught us lessons that informed the next generation of lighting technology. So what does this all mean for us? We've journeyed from the seemingly simple idea of an electrodeless fluorescent lamp through the complex engineering challenges of high frequencies and exotic core materials to the market realities of cost, performance, and fierce competition. Induction lamps were a truly fascinating chapter in lighting history, an engineering marvel that, while not mainstream, offered incredible potential for its time.
Yeah, and what's truly insightful here is how true innovation isn't just about a brilliant idea, but about overcoming practical obstacles, navigating economic realities, and adapting to an ever-evolving technological landscape. It's the story of an amazing solution that just arrived a little too early, or perhaps was overtaken by even faster-moving innovations.
We hope this deep dive into the surprising world of induction lamps has sparked some new curiosity for you, illuminating a corner of technological history you might never have considered.
And here's a final provocative thought for you to mull over. Today, we often see technologies that are considered solved by a dominant solution, much like LEDs and lighting. But considering the rapid obsolescence and constant evolution we witness, what overlooked or niche innovations from today's cutting edge might be the induction lamps of tomorrow. Ideas that are just waiting for a slight shift in material science, a new market need, or maybe an unforeseen problem to truly shine and revolutionize an industry we thought was settled. Something to think about.
Definitely something to think about.
Okay.
Until next time, keep exploring, keep questioning, and keep diving deep into the knowledge that surrounds us.